Yeah, so this is your week 6 of your problem solving session for your statistical mechanics course. So yeah, so we are closing towards the end of your NPTEL course, and so yeah, and there have been most of the topics have been already covered for the course that has been prescribed from the beginning. So yeah, here today we will particularly look into the final topics of the course, and I think also which was also there in your week 6 of your lecture, which is already there in your portal. So so I hope you are going through them regularly and and you are following the lectures and also solving assignments, and yeah, those would be helpful if you are regular enough, because you would be also appearing for a test after the end of this entire course. So yeah, yeah, if you still having any issues or any problems in understanding any concept, or also any solving any questions of the assignment or something, you can always discuss here, ask it. So yeah, please feel free. Yeah, so today we'll talk a little bit about the Ising model, which was discussed last time, and also see some related problems, and could be uh, from the assignments as well. So yeah, what is basically Ising model? Um, the an Ising model is basically a spin chain system. So it's like a collection of spins. So here we are talking about only one-dimensional type system. So uh, and and this just help us to for simplicity, we can start off with this kind of model. So if we go to 2 dimension, 3 dimension, then there could be more things which is also not, I think, the part of your discussion in your course as well. So yeah, so for one-dimensional system, for one-dimensional spin chain system, this Eigen model is one of the simplest model. So it's very I mean, it's better to start always with this kind of spin chain system to understand about the statistical properties that comes out of or thermodynamic properties that comes out of the statistical analysis of this model. So yeah, so again, you can for accurate details, you can go through the lectures which are already there in the portal. So yeah, so Ising model, as I was telling, it is a spin chain system. So yeah, it's a collection of spins. So you can think of there are spins distributed in some lattice uh, at different sites, one by one, and each location there are some spins. So it could be uh, we are talking about only a spin half, let's say, like spin half particles. So these spin half particles are distributed in some one dimensional lattice. So and they can have spin positive half or spin negative half. So depending upon uh, I'm denoting them by this up and down arrows. So yeah, so there could be many infinite spin from one extreme end to the other extreme end. So uh, so yeah, so that is what the spin chain system is, a one-dimensional spin chain system. So spin sigma I, these are each spin you can denote by sigma 1, sigma 2, sigma 3. So sigma 1 is basically plus half h bar, or it could be also minus half h bar. So at a single time, your spin can have only either plus or negative value. So yeah, and the Hamiltonian for this spin chain system can be uh, given by this. So these are your basically your energy. So you can see the first term. Uh, the first term is this minus j sigma I sigma j. So suppose I'm looking at sigma 2, then uh, then it will have a energy, like it comes because of the coupling of its adjacent spins. So when a spin is there, you can think of like it has some interaction with its neighbors. So its neighbors are sigma 1 and sigma 3. So so when I'm talking about sigma 2, it has two neighbors. So and the energy is given as the at a single time it can have you can take sigma 1 times sigma 2 uh, with j is the coupling between these spins, and we take same for all. In this case it can be different as well, but yeah, this is the same j, and this is the interaction energy among these spins. And the other, this is the external field. So this h is your external applied field. So suppose if I'm also applying some external magnetic field to this spin chain system, then it will also have another term contributing to its energy, that is h sigma I. So yeah. um yeah, so this is similar to the like energy that we have also seen last time, like in presence of external magnetic field, we have seen something last time, like what would be the energy of your system. So energy, internal energy of the system, we said it could have due to the spin particles can have some kinetic energy, which would be given by its momentum p square over 2m, and then it will also have if the spin particle is in the presence of a magnetic field, it can also have a energy. This would be given by something mu being its magnetic moment, or you can think of mu is the spin. Mu is related with sigma I. So mu I is related with sigma I. This is pi, and h is your applied field, external applied field. So yeah, so that is what uh, I mean here we are only considering spins located at specific sites. So there are no other uh, like I mean there are no kinetic energies that we are talking about here. So right, so there will be one term which would be from the interaction among this among the neighbors, and if it is placed in an external magnetic field of h, then it would be h of sigma I. So yeah, so there is also a magnetic field h, non-zero. And what is the importance? Like, I mean, why do we really, I mean, looking into this system? Like, because in statistical physics it is of a like a much broader relevance if you study this kind of systems. Because suppose if you talk about phase transitions, like phase transitions, which you know in or which you see in like when you take water also. So water can have like water can attain also three different states. So which you know that, like I mean it can have liquid, solid, or also gaseous state. So and to understand about how the phase transition like takes place in the like in water, so you can study the statistical properties and find out what are the phase transition conditions, like what are the discontinuities, what happens at phase transition point, like what kind of properties like goes wrong, or what really how it is becoming discontinuous. So those phase transitions, like I mean you if you are particularly want to see something in type of a paramagnetic and paramagnetic substance, uh, like uh, you can find that in this kind of Ising model as well. So in Ising model also, which we are explaining in terms of spins, you can also study the phase transitions here as well. So suppose let's say if you have a some magnetic substance, and you are keeping in some you are keeping in some temperature, and then suppose if you are increasing the temperature. So let's say this is your applied magnetic field, and this is your temperature, uh, uh, and in the applied magnetic field you are putting your magnetic substance. So when you increase the temperature, you will find that magnetic substance will lose magnetic field. I mean, you will see that it will have zero magnetic field within the magnetic substance. So it will behave like a paramagnetic. I mean, the overall magnetization will be zero within the material. And but if you reduce the temperature beyond below certain critical threshold value, you'll find that it will have some non-zero magnetic field within the material. It will have some basically it will have some magnetization, and uh, and there you see that that material will behave differently and will basically attain a different state. So that is ferromagnetic. So um, yeah, so if you also see the magnetization of that material over temperature, so as you evolve temperature, so the magnetization will drop and suddenly it will drop to zero at critical temperature, that is the phase transition temperature, and beyond which you will find the magnetization is zero. So, and when the magnetization becomes completely zero, you get a different, basically your material or magnetic material attains a different state. So which you can also explore the all this behavior like using a 1D Ising model also. You can consider this 1D Ising model, and you can study all this phase transition effects, and yeah, and this is important like in various condensed matter problems, and also phase transition is also important from also important in understanding various other like phenomena related with high energy physics as well. So yeah, it forms a very fundamental point in understanding various uh, phenomena. So now, like yeah, so again, like for statistical mechanics, as you know, everything starts from partition function. So if we are given a system like this Ising model, which is defined by this Hamiltonian, so then how to write the partition function? Then so yeah, the partition function, like from the definition, uh, as we, I hope you are already aware of. So which, so the partition function is, so far you have done. So it is given as something minus beta epsilon I, and I is some numbers. That is what here also we are doing. So instead of I, so here it is careful to note that we will sum our different spins. So so uh, this S basically means, so first of all there are um, like, this one minute, this notation one, mm, okay, so here H is basically, mm, so yeah, so this is your H, magnetic field intensity, and your this H is beta times H, and I have also written K. So K is basically beta. So these are some just notations. So because when you do partition function, so you know you uh, have to do something exponential of minus beta energy, or the here which we have the Hamiltonian. So and this beta, so when it is multiplied with the j, and so when it is multiplied with this j and this capital H, so here I will do uh, beta times this h, curly h. So then I have to multiply with beta with the first term and also with the second term. So the first term beta j, that I am taking it as k, and the second term beta capital H, which is your magnetic field intensity. So I am denoting it with small h. So this is your external magnetic field parameter. So and then yeah, and then it is like you will see that this is uh, summed over different spins. So this means like uh, so this is S1, S2 up to Sn. If there are n spins, so they are summed over all the values of the individual spin. So like if I'm summing over S1, uh, S1 can have +1 or -1 value. So again, I will also sum over S2 and S3 and so on up to Sn. So we will see, go through them. So yeah, yeah. So the first thing that we can look over here. So find the partition function in terms of a new variable. Uh, okay. Yeah. You have to find the partition function in terms of a new variable eta I. Uh, just 1 second. Yeah. Uh, So here we have to just write down the particle function like in terms of this eta I. So instead of si, which you see here, the particle function is written in terms of si's. So we have to write in terms of eta I. So and also it is been given that the external field h is taken to be zero. So this h is taken to be zero. That means the small h is also taken to be zero, and this term is not present. So, uh, so yeah, that means your partition function, your z, can be written as summation. So you see, like as I was telling, it is this summation is over for all these pins. So so there is sum over s1, so up to there are sum over sn, and you have exponential uh, k times uh, I equals to 1 to n minus 1, uh, si and si plus 1. So yeah, the first term will not be there. So because your external magnetic field is taken to be zero, and so the coupling term, the coupling energy, the second term will only contribute here. And here I'm taking, you see, I'm taking from s equals to 1 to n minus 1, because uh, suppose if there is a uh, yeah, and one more thing, that there is no constraint on the boundary spin. uh, I mean, so boundary is like open, so there is, it is not like a closed boundary, like it is not periodic boundary. So it is like if I am taking spins starting from this side, and this is the extreme most left hand if you think, and so the spin will stretch the length of the spin chain will stretch to the extreme right, and it will go where there also you find some spin at the end. So which means, so if this is S1 and S2, S3, it will go up to Sn. So and Sn and S1 are not related. So you can see that Sn has only one neighbor, that is Sn minus one. So that is why here you need to be careful. It should go from 1 to n minus 1. So yeah, so for n minus 1, n is the neighbor and also n minus 2 is the neighbor. And for n, it has only n minus 1 neighbor. So yeah, so that is why it will go till n minus 1. And and the new variable which is here defined as eta I. So eta is given as si and si plus 1, where yeah, where I basically goes from 1 to n minus 1. So that means you can write eta I equal to plus 1 uh, if si equal to si plus 1 and minus 1 if si is negative of si plus 1. So these are basically product of two spin halves values. So spin half, it could be either positive plus half or negative minus half. So or right now, if you just think of like plus one or minus one. So each spin value can have plus one or minus one. Like we are talking in terms of only the let's say uh, Bohr magneton units. So it would be plus one or minus one. Uh, so if they are same, if they have same values, if both S1, let's say I is 1, so that means for I1, you will have S1, S2, so that means um, your if your S1 and S2 both have same spin value, like either plus one or both of them will have, or they will have minus one. In that case, your uh, eta one will also remain positive if both the values of the spin are same. If they are different, one is positive and the other negative, then the eta one will be negative value. So that is what. So it will eta I will have two values depending upon these two cases. So yeah, and so now what you can do here. So um, and also you will see here. Um, mm, Here Si plus 1 is also can be written as uh, eta I times Si. So it's like if I'm multiplying Si on both the sides, uh, on your LHS and RHS, so you will find Si eta I on the LHS, and on the right Si square Si plus 1. So and your Si square will be plus 1 because Si can have either plus 1 or minus 1 value. So Si square is basically your positive, that is plus 1. So that means plus 1 times Si plus 1, or that is Si plus 1 equals to eta I Si. So what I can write here is if I is equals to 1, so that means S2. I can write S2 as uh, eta 1 S1. So, and likewise, if I write S3, so it will be eta 2 S2. And if you see S2 from here, I can write S2 will be eta 2 eta 1 S1, and so on. You will find if there is uh, SI here, so it would be something. Uh, uh, yeah, if it is something SI, or let's say uh, uh, SK, it would be something eta k minus 1, eta k minus 2, and dot dot up to eta 1 S1. So this is something always can be written. So with that, we can write the partition function finally here as uh, if you have any issues or any problem, so please you can speak and you can ask it. Yeah, so the particle function, which here, which we have written here, so that will change it. Uh, so here you see in the summation index, you see the summation was going for all individual strings. So S1, so you have S1 here and Sn. So and they will now change this. So your if you take S1, uh, so your S1 remains as it is, but your but you will have uh, eta 1 and up to eta 2, up to eta n, or basically eta n minus 1. So for uh, s let me write this instead of just being consistent with the notation. So yeah, n minus 1 n minus 2. So yeah, and now in the exponential you have uh, k times so k, it is summed over si plus 1, so that means uh, eta I, it is summed over eta I. So it is summed over eta I, and I goes from 1 to n minus 1, so that will be uh, okay, summed over eta I, and that is what. So yeah, and that is what you can write it as S1 eta eta 1 up to eta n minus 1, and it is summed over all the eta ith index. So that means it will be eta 1 eta 2 uh, plus up to, so yeah, n minus 1. And then okay, and further what you can do here, so since it is uh, summed for each eta values. So let's say if I'm writing for eta 1, it will be exponential of k eta 1. Then for eta 2, I will have exponential of k eta 2. Then and so on, like it will go up to uh, n minus ones. So it will be exponential of k eta n minus 1. And now each eta value can take either plus or minus depending upon this which we said. So it can have plus 1 or minus 1. So just like how spin values were also, just like how SI values of SI is also plus 1 or minus 1. So eta is also constrained to have plus 1 or minus 1. So and that will make things bit convenient for us. So if you see here, so the S1, the summation S1 which is hanging around on the outset, so that is just simply the sum term, or really see what is exact. So yeah, so if I put the values of eta 1 will be either positive or negative. So it can have plus k or minus k, and from here also I will get plus k minus k, and so this is like I will have summation or s1 uh, k plus exponential minus k up to n minus 1, and and this this is just summation, as we have seen. So this extra sum comes because of the open boundary condition or the no constraint system that we are considering. So and s1, since s1 is also like mm, uh, yeah, so it is like you can understand or you can think of like maybe um, like for yeah, just 1 minute. Yeah, so I was talking about S1 over here. So S1 is just like the extra summation that like hangs around because of the open boundary that we have taken. So so it will just simply add because I mean S1 again has two values, which is S1 could be either plus 1 or minus 1. So it is like I will have uh, one term for s1 equal to plus 1 value and one term for the s1 equal to minus 1 value, and I have to add them. So so this will become uh, exponential of k minus ek times n minus 1, again plus exponential of k plus e minus k n minus 1. So two times I have to add because s1 can have two values, so it is like exponential of k plus minus k n minus 1. And yeah, so in general also if you just write simply s1, uh, it is basically 2. So s1 can have either plus 1 or minus 1. So if there is nothing present, so no there is no term in this expression with having s1 then that means you are summing over just value 1. So summing over value 1, it's just basically summing uh, them the same thing over and over till the number of times, till the number of values that S1 index has. So S1 index here has two values. So that is why you will add two twice. So that is why we have twice of this vector. And further, I can also write this exponential k and plus exponential minus k in terms of hyperbolic function or cos trigonometric hyperbolic. I can write it as 2 cos hyperbolic k times n minus 1. So yeah, so this is what it will become, the partition function for your Ising model. So if any doubts in this or any question you can ask. Uh, I can't in little so yeah, I'm having a bit low battery on my device, so let me just connect it in a moment. Uh, yeah. So next we can see the like a similar thing right here. So we'll try to find the same partition function now with the boundary condition with this. So that is a periodic boundary condition. So now we have constraint on the boundary. So now how this partition function will change. So so in this case, and again, like we can take uh, h equals to 0 also here also. So then, um, so yeah, so the partition function here in this case, you can write it down as z sum over s1 to sn uh, exponential. So k and the summation goes from I equals to 1 to n minus 1. So si and si plus 1. And here you see that like this is the same thing which we written here as well. So note here that there here we were taking the summation up to n minus 1 because that is the thing as I was trying to highlight at the beginning that the boundaries were open, so they do not have any constraint. So it will terminate in n minus 1. So the sum was going from 1 till n minus 1, but here it can also go to n. So the nth term will basically, so up to n minus 1 things will remain as it is, but for the nth it can also go to nth term. So the nth term will have plus k. So I'm just separately writing down the, instead of writing in the summation, I'm separately writing what is the nth term. So the nth term will be this, the interaction of the first and the last spin of the lattice. So because it's a closed periodic boundary type. So and now so again here also the uh, we have to consider this different parameter, different, uh, I mean, this new variable eta. In terms of eta, we have to write down, or we have to find out the partition function. So here also eta is defined in the same way. So, but in this case, your uh, basically uh, eta will changes. So let uh, so so if I write Sn and S1, then your eta, in terms of eta, it would be eta 1, eta 2, up to eta n minus 1. And yeah, so it will be eta n minus 1, because if you remember last time, as we have shown here, so Sn is given to be this. Uh, so, so this is Sn. So, okay, I've written in the wrong place. So this is Sn as we saw last time. Now, if I write down what is Sn S1, so that will be this. Yeah, so Sn S1 is this, because again uh, S1 square is 1. Um, so now again in terms of eta, you can write down the partition function, that is z. Uh, uh, Now there will be no separate S1 right here. So now suppose like I can here even Sn S1, I can denote it as something eta 0. So the summation will go from eta 0 uh, till eta n minus 1. and and if you see the inside the exponential, you have k eta 1 plus eta 2, and this goes till or let me just write down again. So first we have 1 to n minus term for eta I, and then further we have one more additional term, that is k sns1. So k sns1, which we have written down here, that will be eta 1, eta 2, up to eta n minus 1. So eta 0 to eta n minus 1. uh, so that is exponential k eta 1 plus eta 2 plus up to eta n minus 1. Then again you have plus k times eta 1, eta 2, up to eta n minus 1. Yeah, and now so what you can do exactly here, Um so this eta 0 which I have written, so that is the same. Yeah. So this uh, eta 0 here works in the same way like last time as we checked for what is S1. So this eta 0 I am defining for S1. So last time uh, here we had one extra S1 hanging around. So so now that S1, like we are still keeping it, but now we are keeping it by just a different notation, just to be bit consistent more, because we are denoting everything in eta. So I'm denoting S1 as something eta 0. And then here what we can do here. So if I split this summation, then again I will have a overall factor of 2, and then uh, the other summations will contribute from this eta 1 till eta n minus 1. um, and then uh, from exponential, let me just retrieve the first part. So that is this which we had last time also. And then and also I will have exponential of this k eta 1 and to eta n minus 1, and this I can further write it as uh, n minus 1 exponential k eta 1 eta 2 up to eta n minus 1. And here in the last factor, this last exponential, I can write it down as a exponential series, or basically like expanding out the exponential. So which yeah, I mean basically Taylor series kind of thing. So it's basically I can write in this way, uh, k eta 1 up to eta n minus 1 alpha or alpha factorial. So just like I mean using the idea of exponential of x, that is alpha 0 to infinite uh, x alpha or alpha factorial. So, yeah. And now more or less we are getting what would be the partition function. So that will be alpha equals to 0 to infinite. Uh, so k alpha and our alpha factorial, the constants you can pull them out, and the eta values. So for the etas I can write them as, and the rest you can see, you can check this, you can write it as summation over eta alpha uh, times exponential ek eta times n minus 1. Yeah. And then further here I can also write uh, this, we can simplify this further as twice of summation alpha going from 0 to infinite, uh, k alpha over alpha factorial. Uh, uh, so again, eta can have either positive or negative value. So for eta equals to plus 1, you have uh, exponential of k, uh, and for eta equals to negative, so depending upon value of alpha, you will have minus 1 to the power alpha. So so you cannot directly take negative here. So it depends on the value of alpha. So and exponential of minus k. So yeah, so you put values of eta, that is either plus 1 or minus 1. So from there you have these two terms, and this is again to the power n minus 1. So and the same way, if you see, like you can in terms of hyperbolic function as we written earlier. So like as we got to cos hyperbolic k. So here also you will have something similar. So for all like even alpha values, so you will have cos hyperbolic terms will contribute, and for all uh, odd hyperbolic values, you will find that uh, negative. You will find that sine hyperbolic term will contribute. So, like for example, this will go something as if I write it down, suppose 2 times, let's say alpha equals to 0, I will have uh, for alpha equals to 0, I will have exponential k plus exponential minus k, uh, yeah, exponential of k times exponential minus k, then uh, n minus 1, uh, and for alpha equals to 1, I will have uh, so like here maybe I can let me see. So yeah, it is right. You will get both cos hyperbolic and sine hyperbolic. Uh, Let me check. Uh, okay, so you can check that it is basically an expansion. So um, so for odd alphas, you will have something exponential of k minus exponential minus k. So that will correspond to something sine hyperbolic k, and for even alphas, so it will correspond to something this cos hyperbolic k. So this you can write it down. In terms of the following expression, so you can check upon expanding, it will be basically this 2 sine hyperbolic k. And so upon changing the boundary condition. You see, like earlier, you just had twice of cos hyperbolic k, twice the, uh, twice of 2 cos hyperbolic k to the power n minus 1. But now, instead of twice, you have two hyperbolic terms, and they are each individual to the power n. Yeah, that is right. Uh, Now we can see what are free energies, and see in both the cases, like what is exactly the difference and how this would be. So okay, so if you have any questions, you can ask. Okay, for free energy, uh, for free energy, it is given as minus kVt ln your partition function z. So now, if you take ln z, so suppose you take ln z uh, for the initial case when you had so for the z you had two, so you have z equals to twice of 2 cos hyperbolic k to the power n minus 1. So ln z will be your ln 2 plus n minus 1. So using just the logarithm properties here, you will simply get this. Uh, right. So further here I can also uh, so this is ln 2 n minus 1 ln2 plus ln cos hyperbolic k. So then we have n ln2 plus n minus 1 ln cos hyperbolic k. Uh, right. And further, So so now if I write down what is free energy, then it would be minus kT ln z. So that is minus kT n ln 2 plus n minus 1 ln cos hyperbolic k. So this will be simply minus n kT. If you pull out the n outside, so it would be ln 2. Uh, so it would be uh, ln 2 n minus 1 over n, because I'm taking the n outside. So this is cos hyperbolic k, and so this will become yeah. So yeah, this is what f you will get. Uh, but now if you see one thing right here, if I take the limit, the thermodynamic limit, that is the uh, n, that is for a large n going to infinite, I can write the free energy is minus n kT. Uh, uh, I can write it as ln2 plus 1 minus 1 over n ln cos hyperbolic k. So this is like minus n kT ln2 cos hyperbolic k plus order of 1 over n. So yeah, and it is interesting to note down here, even uh, in this n tending to large limit. Uh, so even if I would have used the partition function of periodic boundary condition, so uh, so this will remain, it will remain same in this limit even when uh, z is calculated using the periodic boundary condition. Because I mean here if you see the free energy that we have calculated here, so we have calculated using this no boundary condition. So here we have no boundary condition, no periodic boundary condition. So yeah, maybe I can just no periodic boundary condition. So it basically means like uh, free. Like free boundaries remove exactly uh, uh, free boundaries. So, so in the thermodynamic limit, we can say that in thermodynamic limit, the boundary condition is negligible. The effect of boundary condition is basically negligible. Yeah. So now, so now there is one more method to uh, like I mean, so far if you see like whatever we have done, like the approach that we have calculated the partition function in terms of a by defining a new variable which is eta I, and in terms of that we are taking the sums and finding out the partition function. So and we are all doing this by keeping or making when the external field is zero. So, but if you do this for case of non-zero external field, like it would be very like difficult to have to do this kind of ad hoc calculations. So for that, like there is another better way to do that, and that is what is also known as transfer matrix method, and that will also generalize the this way of calculating the partition function. So and we will and we can use h not equals to 0. So the condition that we have been using here. So uh, for for this h equals to 0, now we can also do for h which is when not 0. So and that is the method of transfer matrix. So yeah, when h is not 0, so by that the I mean, yeah, so when your h is not 0, so you have one more term in this argument of your exponential. This is basically your total uh, partition function. Uh, so okay, one second. Yeah, so for uh, h not equals to 0 case, so these are all what you can have. Uh, uh, so so your partition function will now like you can write down or you can expand them like term by term. So in this way. So first here, um, Okay. So here this is your total uh, partition function which you write down from the general Hamiltonian where you do not also have your external field to be zero. Then from there, like you can write it in this way. So I can let's say so the first for let's say uh, in this case I have I equals to 1. Then for I equals to 1, I will have this term exponential of h s1 plus k. Basically, I'm just writing the argument of exponential. Let's say hs1 plus k times h1 h2. Uh, but this I can also write down. Let's say this is what you will get for I equals to 1, and for I equals to 2 you will get something hs2 plus ks2 s3. And now if here what I can do, uh, so I can write this hs1 as something as uh, h by 2 s1 plus h by 2 s1. And for also I equal to 2, I can also write h by 2 s2 plus h by 2 s2. and then I can take h by 2 s1 plus h by 2 h2, and k s1 s2 will give me this thing. So likewise, I can break this all HS1s, HS2, and like there will be HS3 into HS1, like into halves. So like HS1, I can write it as H by 2 S1 plus H by 2 S1. So then one of these H by 2 S1 will go to the next successive uh, I equal to term, which you can regroup them. So it is like I'm regrouping this the partition function which I have written here, and if you regroup all of them, you will find something like this. Now you will see there is a pattern right here. So yeah, this is something a factor which has dependence on S1 and S2, and this is on S2 and S3, and this is on S and S1. And likewise you have all such um, pairs of spins, and these pairs of spins contribute to some each like factors in the partition function, and I can write down them as some kind of matrix element. So a matrix element also like comes with two indices. So here I can treat the two spin pairs, or basically a particular given spin pair corresponding to a matrix element. So and that is I'm denoting as TS12. So if I denote it this way, I can write down a matrix like suppose in yeah I can write down depending on S1 and S2, I can have T11, T1 minus 1. So here S1 can have plus 1 minus 1, and also S2 can have plus 1 minus 1. And so likewise I can write down a matrix uh, for this uh, met, uh, yeah for this matrix T, and then each of them like it will be equal to something exponential of h plus k, exponential of minus k, for when uh, s1 is 1 and s2 is minus 1. And likewise you will also get for s when s1 is minus 1 and s2 is plus 1, and now here you get minus h plus k. So then you can write down the matrix element, or you can write down the partition function, the complete total partition function. in terms of H and Ks, that will be S1 over all the spins. So you have T S1, S2, T S2, S3, so T S3, S4, and up to T Sn, S1. So now, like if you see here, so this is like uh, so like if you think of a matrix which is like basically given as something uh, a product of some other matrices B and C, then it is in terms of elements. You can write down this matrix elements of A as A Ising as something uh, summing over K for B having indices Ik and C having indices Kz. So the same thing if you observe here also, or basically if you also take trace of A, that is basically sum over all the i's for A II elements. So now if you see, like this is the idea of how matrix elements can be expressed. The same thing if you observe for this thing right here. So here, I mean, the sum which is taken for all individual spins S1 from S1 to Sn, and um, then it is done for each individual TS1, TS2, 3. So it is like you are taking matrix elements. So and S1 is summed over and Sn is summed over. Just like here, we have seen K is summed over when we are doing this matrix matrix multiplication of B and C, and that gives something AIZ. So here everything is basically summed out, even S1 and Sn. So that means it is something related to trace. So when everything is summed out, like for a given matrix, so like that is what we do in trace. So while taking the trace, we sum over all the diagonal elements. So here also it will happen the same, because if you see only the S2, S3, S3, S4, if you leave out the S1, it will look like something like a matrix and matrix multiplication first, because uh, if you see only the first two thing, that is T S1 S2 and T S2 S3, so it is like you have something T tilde S1 and S3, but and then it will repeat again for other successive elements that you have, and then these are again all your matrix multiplications, and once you reach the end you will find that it would be something like p, like it would be something uh, or I can write some different, some t prime S1 S1, and this is also again summed over. So that means your partition function, I mean this one, this S1 S1 is also again summed over by S1. So uh, yeah, so that is why you can write down your partition function as summation S1 TS1 S1 to the power n, because uh, uh, if you multiply TS1 S2 and TS2, this is TS2 S3. So that gives you uh, that basically gives you this T tilde S1 S3. So that is basically T square. We are taking the T square. And same if you do it once more again with TS3H4. So this is TS3H4. Uh, so you are doing like t to the power cube, and likewise when you do the complete thing, it will be t to the power n. So and then you'll find it is everything is summed over s1. So this is like some let's say t prime or t tilde s1 s3, and again if you do this too, you'll find something like t tilde t tilde S1, S4, and after all, you will find this is something will be t to the power n, or I can also write it as t square S1, S3. This is also I can write something as t cube S1, S4. This is I can write it as t to the power n. So when these two are multiplied, so it will be t to the power n S1 S4. So and that is basically, and you have summation again for S1, that is trace of t to the power n. Now, now it becomes quite easy for you. So now you just have to deal with this transfer matrix only. So once you write down the transfer matrix, then like by just taking the trace, you can get the uh, partition function. So even for the case when magnetic field is not zero. So, and again for trace, for taking the suppose if lambda 1 and lambda 2 are the eigenvalues of t, then you can write trace of tn as something lambda 1 to the power n plus lambda 2 to the power n. So yeah, so after all, you just need the eigenvalue in the information about the eigenvalues of transfer matrix, and that can give you the partition function. So now we can see the uh, so using the transfer matrix method, find out the free energy, and the thermodynamic. So thermodynamic limit is again your n much bigger. So yeah, so the transfer matrix which we had, yeah, so the transfer matrix which we just discussed right now. So it is given as for uh, the given Hamiltonian. So the Hamiltonian like the for let me of the Ising model of the gen. So of the 1D of the Ising model with h not equals to 0. So with h not equals to 0 in the thermodynamic limit. So so the we do it for the general case. So like the transfer matrix we just which what we just discussed. So we have to use the same transfer matrix here. So so the same transfer matrix was uh, this exponential of h plus k, uh, then exponential of minus k, and exponential of minus h plus k. Yeah, so now using this transfer matrix, so we have the transfer matrix. So to get the so for free energy again, we want this for free energy we want minus yeah. So for free energy we need to do minus kbt ln of partition function. So again we need the partition function. So the partition function here uh, is uh, trace of transfer matrix to the power n, and this is lambda 1 to the power n plus lambda 2 to the power n. So yeah, and so suppose if I assume if lambda 1 is bigger than lambda 2, one of the eigenvalues is bigger than the other, the lambda 1, then the partition function I can write in this way: lambda 1 to the power n plus uh, yeah, if I take lambda 1 to the power n, the overall vector, then I have this. Then in thermodynamic limit, it will be just basically z lambda 1 so to the power n 1 plus uh, So, so I can write it as 1 plus order of exponential minus alpha n. And what is alpha here? So alpha is this log or ln of lambda 1 over lambda 2. So which is some positive constant. So the idea here is to note here the only the largest eigenvalue. So only the largest eigenvalue uh, eigenvalue of transfer matrix uh, dominates in the thermodynamic limit. So now here again, so after we need the eigenvalue, so whether the larger or the smaller, so we need to calculate the eigenvalue. So you can just do the usual conventional calculation of computing the eigenvalues. So first you take the determinant of the characteristic uh, equation. Yeah. So you basically need the characteristic equation, and you have to solve for its root, and the roots will basically give the uh, eigenvalues. So, so the characteristic equation of the determinant of exponential x plus. So for for eigenvalues, you take determinant of exponential x plus k minus lambda, not k, minus lambda minus k. So, so basically you need to do this determinant of t minus lambda I equals to 0. You have to solve this. So minus h plus k minus lambda equals to 0. Then, so when you solve this characteristic equation, so you get lambda. You basically get a uh, polynomial equation, and the roots will be uh, so 1 and 2. It will be exponential k cos hyperbolic h plus or minus uh, sine hyperbolic square h plus exponential minus 4k. And since we only want the largest eigenvalue, so the largest eigenvalue will be the one with a relative with a positive sign between these two terms. I mean the cos hyperbolic h plus square root of the inside whatever present. So that will be the largest eigenvalue. So your free energy would be given by just simply minus kVt uh, kVt um, so yeah, so you can just take your partition function to be lambda 1 to the n in the thermodynamic limit. uh, so ln z, that will give you minus n kut, ln of exponential k cos hyperbolic h plus sin hyperbolic square h plus exponential minus 4k. Yeah. So here if you see, even here if you make h going to 0, uh, you will also get the result 1 with the uh, result that we got. So that is uh, so here you can see that it will go towards cos hyperbolic k, the one which we did last time. So it is also reducing to the tending to 0 limit as well. Yeah. Now, like there is this thing, something which probably you would have also seen in like today's. I mean, in the last week's discussion, there has been also something about mean field theory, which has been also discussed. Uh, so that is like you basically using the effective you define some effective Hamiltonian, and using that you find out the this thermodynamic properties. So like we can uh, um, mean field approach. So in mean field approach, what you do, like suppose again, if you are like if you want to do the same free energy calculation, you have to calculate through the mean field approach first. Uh, like what you generally do with that. Uh, Wait a second. Let me check. Yeah, so for yeah, so in Winfield approximation, so uh, we basically we write the magnetization, the magnetization as the following average. So that is magnetization. Let's say this is magnetization per site. Magnetization. Uh, Basically, here it means magnetic moment per site. Magnetic moment per site. Uh, so it will be given as something n number of up spins minus number of down spins uh, divided by n, uh, and this is yeah. So this is the average of the magnetic moment, average of the spins, the spin sides are taken to be something, some value n. This is your mean value, and using this mean value, so we can also express what will be your number of upspins. So your total number of spins are n. That means your n up will be basically 1 minus uh, uh, or n minus n down. So and this you can also write it as n of 1 plus n over 2. So the number of the total uh, number of uh, configurations with n up is basically omega. It would be something uh, n combinations. So that will be n uh, factorial over n up factorial, then n minus n up factorial. So this is so if you know the number of configurations, so you can calculate the Boltzmann entropy. which can be given as s uh, n uh, log of omega. So and we know what it will be in terms of m, in terms of magnetization. We already know what would be your n's. So with that you can write uh, n times ln2 plus minus half. You'll check that like if, using the relation of n up here, you can get 1 plus m, uh, then log of 1 plus m minus half 1 minus 1 minus m log of 1 minus m. Right. So likewise, you have the entropy. You can also calculate internal energy in terms of m again, which would be minus j summation over ij side m squared minus h summation m. So sigma and sigma j, which was earlier used to be there in the Hamiltonian, I'm replacing them with m. So basically, here the idea is the energy per side. We basically imagine replacing every sigma in the Hamiltonian on every side. So here we can write. So so for the idea here is to express uh, all properties all properties in terms of following terms in the following term in the following or yeah. So then internal energy. So here we replace uh, all energy per side uh, sigma I with sigma the mean value to the average. So right, and so that means, but there will be, we know, the summation used to control the number of terms that is appearing the for the to account the neighbors of the given set. Now this will give a some coordination number, so that is basically the number of neighborings. So uh, let's say the coordination number, the number of neighbors will be governed through let's say u is given as minus z is there. Uh, so z by 2 m square minus h. So here z uh, is the number of neighbors per side, number of neighbors per side. So so now finally you can write down the free energy which is given as u minus ts. So we have expressed everything all in terms of m. So now your free energy, if you see, it can be uh, uh, so let's say I'm writing in terms of uh, free energy per site. So that means upon total n. So if I do that, um, and also remember, so this one which I have written, so this is u over n. So this is not uh, the total uh, here. So so there you will find this would be something given as minus jzm square over 2 um, minus hm, then the entropy which you have, sorry, minus t ln 2 minus half 1 plus n ln 1 plus n minus half 1 minus n ln 1 minus n. So and suppose if I'm denoting this as small f. So now if you if you extremize this free energy, the free energy in which uh, it attains a extremum value for a given value of m. If I find out, so what I will get, extremizing m, extremizing f. So this will give me minus jmz. Uh, so maybe I can replace this get something with else. It may get confused with partition function notation. Okay, right. So d ln of 1 plus m minus 1 m equals to 0, and you see that you get this magnetization value where it gets extremizes. So this is this j n d plus h over t. And and if you see, if I call the numerator of this argument of 10 hyperbolic as something effective Hamiltonian, that effective field, uh, this is, suppose if I call this some effective field over t, then this is what my magnetization would look like. And if you recall, even last time, even we have discussed this. This is something similar to the ferromagnets that we have discussed last time, which we have also done some problems in brains of some external field. We also got some kind of this transcendental type relation. So suppose you want to so remind, I can, yeah. So if you recall last time around, we also did something. We also found something of this form. So here you see this is the magnetization that we were looking into, and that is proportional to this h. H is the applied field, and now we are getting the same thing, but with mean field approximation. So from mean field approximation, we are also getting something of the similar type of magnetization that we got last time as well. So so here, uh, so making a mean field approximation, the effective field is making a mean field approximation. The effective field is given as effective equal to JMD plus H. So suppose if uh, we can do a quick maybe. So like something similar that you can also find in one of your problems as well. So using this main field, using the main field approximation, uh, estimate the uh, mean field, estimate the mean spin value. So in this Ising model of Ising model, so there again you can use this. So this mean value of SI basically means the you need to take the average of single spin average. So this single spin average you can write down in terms of mean field approximation that which we have done. So this will be spin so SI, which will take uh, either S equals to 0 or uh, let's say you are we are talking about S equals let's say your SI takes 0 and 1, then from your mean field you can write down as this exponential of beta uh, is there yeah. So beta so beta jm uh, d plus h uh, yeah. So then uh, in denominator also you have something exponential beta. So this will be times uh, h effective. So this will be times si. So again here we are not right. Yeah. So this will be your effective Hamiltonian. So if this is your effective field. Then your effective Hamiltonian will be something h effective si. So summation of h effective si. So then HMD plus uh, HSL. So if you solve this, like I mean, yeah, it's simple to see. So you will get something uh, SI to be uh, exponential of beta uh, ZD plus H, then 1 plus uh, 1 plus exponential of beta ZD plus H. So this is something you will also find. Um, so in one of your questions which you can check. So yeah, so this mean field approximation, this is how it works. So yeah, this is how the different ways which you can do this analysis of Ising model, and from this statistical mechanics, you can find out the thermodynamic properties in these many ways, and you can interpret them in various contexts. Yeah. So yeah, I think we have also uh, uh, like ended right at the time, so we can stop right here. And if there's any question, anything, any problem, you can uh, let me know. Okay, if there's no question, then we can probably end it right here. Okay, so yeah, we'll again discuss next time, like this week. We'll have the another problem solving session, and then probably we may have one or two more sessions to conclude this entire problem solving sessions of your of this course, and also that will also conclude like everything uh, for the like course training that you need for this NPTEL test that you'll be having after the end of this course officially. Yeah, so yeah, try to get them like clear as soon as possible before you appear for the test. Yeah, so yeah, that's it. So we can meet again next time. So yeah, thank you.